when we first learn how to deal with AC signals, AC voltages, AC currents, how to operate on them mathematically, there are two ways in which we can analyze them. One is the algebraic method, in which we look at these equations in terms of trigonometric functions. The other is the phasor representation method, in which we can describe these signals graphically. Now, both these methods have their own strengths and weaknesses, and we will use them together in order to come to a better understanding of how AC circuits function. So, what exactly is a phasor? Remember that in an AC circuit, the voltage and the current are changing all the time, but they are alternating between two values, the max positive value and the max negative value. If you were to describe it mathematically, you would say that the voltage and current in an AC circuit is varying sinusoidally. But showing a sinusoid all the time is not practical or very elegant. So, we discover a unique and interesting property of these signals. We can describe a sinusoid, any sinusoid, as the rotation of a vector along a circular path. Please remember, voltage and current are not vector quantities. These are not vectors, but they can be represented using a rotating vector, which is called a phasor. Let us see how we do this and how we can use phasor representation to make visualizing these signals a little bit easier. So, here we have a circle. Let's call it a unit circle, which has a radius of exactly 1. We can visualize a vector which has its origin at the center of this circle. So, here we are drawing a vector. Here is our vector, and this vector is free to rotate along the fixed center on this circle. So, it is tracing this green circle on these two axes. So, here we see that this vector is able to freely move or rotate in this manner. Now, we have to see how we can describe this behavior in terms of a sinusoid. Let's say that this vector has rotated by a particular amount. So, it has gone through an angular displacement. So, this is our angular displacement, and the length of this vector is still unit, it is still 1. This vector can now be reduced or decomposed into its horizontal component and its vertical component. So, we can make projections from this vector. So, here is one projection and here is the other projection. Now, if we say that this vector has the symbol V, we can say that this vector is rotating freely on this circle, and as it goes up, as it is moving from 0 degrees or 0 radians to 90 degrees or pi by 2 radians, we notice that the horizontal component of this vector is progressively becoming larger and larger. Now, if we define this rotating vector as V, we can resolve this into its horizontal and vertical components. As this vector rotates from 0 radians to pi by 2 radians, we observe that progressively the horizontal component of this vector is becoming smaller and smaller. You will notice that the projection of this vector on the horizontal axis becomes smaller and smaller, and as this vector reaches pi by 2 radians, so if the vector becomes vertical, the horizontal projection of this vector becomes 0. On the other hand, we also notice that as this vector is rotating from 0 to 90, the vertical component of this vector is progressively increasing. We can display this behavior by stretching out the angles into the horizontal axis. So, we can translate the motion of this vector in terms of the change in its horizontal component and its vertical component as a function of angle. So, here on the other side we have a new graph, and this graph has its horizontal axis in terms of angle, that is the angular displacement of this vector. So, if we were to simply look at the height of the vertical component of this vector as a function of theta, we see that when the vector is pointing exactly along the x-axis, the angle it is making with the x-axis is 0. The height of this vector or the component, the vertical component of this vector for theta equal to 0 degrees is 0. So we can say that for theta is equal to 0, that is the origin of the second graph, the height of this vector is also 0. On the other hand, when this vector rotates to pi by 2 radians, so here we mark a point, pi by 2 radians, we notice that the vertical component of this vector is maximized, it reaches its maximum value. So we can trace that value here. And this is the point where the vector has its maximum vertical displacement. For any of the values between 0 and 90 or 0 and pi by 2 radians, we notice that the vector is varying, it is increasing. So here we see that the height of the vector is increasing. So we can draw it out like this. And beyond 90 degrees, beyond pi by 2 radians, as we continue to rotate the vector, we see that the height of the vector, or we can say the vertical component of this vector, starts to decrease. So it is becoming smaller and smaller. So again, if we produce this graph further, all the way to pi radian, we see that gradually the height of this vector is decreasing until it again reaches the value of 0. Here, the vertical component of this vector again becomes 0 for theta is equal to pi radian. We can perform the same operation for the lower two quadrants of the circle and we will get a graph that looks like this. What does this graph remind you of? Well, this is exactly the graph of the sine function. So we can say that the vertical component of this vector, we can say that Vy, that is the vertical component, is changing according to the value, the scalar value of V multiplied by sine theta, that is the instantaneous angle of the vector at that moment in time. Now remember, this vector is continuously rotating on this plane, on this circular path. So it is completing a given number of rotations every second. So if it completes 2 pi rotation, that is, it goes through one circle, that corresponds to one complete cycle of the sinusoid. So this complete rotation corresponds to one complete cycle of the sinusoidal signal. In an actual circuit, you notice that the instantaneous value of the voltage or the current is following this trend. It is going from 0 to a maximum peak value, again to 0 to a negative peak value, then again to 0, and it is repeating this process again and again. You can imagine that as this vector rotating again and again on the same path at a particular number of degrees per second, which is what we call the angular frequency given by omega. So we can say that Vy, that is the vertical component of this vector, is equal to the magnitude, the maximum value of V multiplied by sine omega t, where omega is the angular frequency of this signal.
Manorama Horizon. Learning made simple.